So we want to turn now to the subject of derivatives of inverse trig functions. This corresponds to section 3.9 in the Thomas textbook, but it's actually just kind of a continuation of the previous two sections because we've just been talking about inverse functions, and we're just going to use a little bit of implicit differentiation to find these inverse trig functions. So first of all, let me remind you of what we know about the inverse trig functions. This was really covered both in your pre-calc class and in the chapter 1 review that we did at the very beginning of this course. So, um, first of all, we have these are there's an inverse trig function for all six of the trig functions, but the three main ones that everyone remembers are arcsine, arccosine, and arctangent. Recall that arcsine, which we write as sine with a -1 exponent above it, it doesn't actually mean the reciprocal of sine. We just write it this way to mean the inverse of the sine function, is the angle in the interval -pi/2 to pi/2 whose sine is x. That's what arcsine of x means. Similarly, arccosine of x is the angle in the interval 0 to pi whose cosine is x. We covered in chapter 1 why we have to define the interval a little bit differently for cosine. I don't want to go over that again. So you just go and review chapter 1 if you forgot about that. And arctan, written again as tan with a -1 symbol above it, is the angle in the open interval -pi/2 to pi/2 whose tangent is x. We can't actually include -pi/2 and pi/2 themselves in the interval because the tangent of -pi/2 and pi/2 are both undefined. The function is infinite at those numbers. So just recall the type of problem that we actually did in chapter 1, because this comes up again a little bit in this section. Get a little bit of review time for that. So let's suppose that theta is equal to arcsine of 3/4. What is the cosine of theta? The way we did that was we said if theta is equal to the sine of it's the arcsine of 3/4, then that means that there must be some triangle where the ratio of the opposite to the hypotenuse is 3/4, and that means that this third sine here is going to be 4 squared by the Pythagorean theorem is going to be 4 squared minus 3 squared. That's 16 minus 9, so that's the square root of 7. That means that cosine of theta is equal to the adjacent over the hypotenuse, which was just √7/4. So that's a typical thing that we did with inverse trig functions. Now, having done that, having done a little bit of review, let's get to the calculus of inverse trig functions. We also covered something that looked like this, but it comes up again in this chapter. Consider the limit as x approaches -infinity of arctan of x. The only real way to do this with the inverse trig functions is to know what their graphs look like. And if you look in the textbook, they have pictures of the graphs of all the inverse trig functions. Um, so the graph of arctan is really sort of like the graph of one branch of tangent turned on its side. So the arctan function looks like this. This is y equals arctan of x, and the horizontal asymptotes are at pi/2 and -pi/2. So you can easily see from this graph that the limit as x approaches -infinity going in that direction is just that the horizontal asymptote right down here, and that limit is -pi/2. If you forget what this graph looks like, just keep in mind that the graph of tangent itself looked like this. But of course, we had to restrict its domain. It had all these repetitions and asymptotes. We had to restrict its domain to just this part of the x-axis from -pi/2 to pi/2. So you'll see that the arctan function is really just kind of like a version of flipping over this one branch of the tangent function. And that's where we get that from.